Understanding and applying the remainder theorem. Let's evaluate a function at a specific input value. Given the polynomial function f of x, defined here, we're told to evaluate f of 5. That means find the value of the function at x equals 5. So we're going to substitute. Everywhere we see an x in the function, we'll put 5. Now we'll use order of operations. We'll do exponents first, then we'll do multiplication, and then we'll add and subtract from left to right, and we'll get an answer f of 5 equals 88,372. In other words, the value of the function at x equals 5 is 88,372. Graphically, this means the function passes through this point, 5, 88,372. So I could check that by typing the f of x, the given function, into Desmos.com or some other graphing utility. And I would notice after I typed in the function and it was graphed that indeed the function passes through the point 5, 88,372. So what I'm interested in doing, considering with you, is to use synthetic division to divide this same polynomial function, f of x, by the input value of 5. And let's consider what the remainder of that synthetic division problem will represent. So we're going to take our polynomial function, the same one as the previous slide. We're going to use synthetic division to divide f of x by x minus 5. Recall, if the remainder is 0, then that means the divisor would be a factor, and so 5 would be a root. How we use synthetic division is we consider the given function in standard form, and we list each of the coefficients of the terms, and we include 0 placeholders. So the synthetic division starts like this: 1 for x to the 7th, plus 1x to the 6th, and then minus 2 goes with x to the 5th. 0 would be the coefficient of x to the 4th. 7, x cubed. 0 is the coefficient of x squared. 0 is the coefficient of x, and minus 3 is the constant term. We're dividing by 5. Synthetic division, recall, goes this way. We take the first number, the 1, and we bring it straight down. We multiply this by 5 to get 5, and we add this column. Again, multiplying this number 6 by 5, the divisor, to get 30, and we add this column to get 28. 28 times 5 is 140. We add the column, multiply 140 by 5, and we add to get 707. Multiply that by 5. We add, multiply that by 5, and add to 0, and finally multiply this last number by 5. When we add with negative 3, we get a remainder of 88,372. And that number should look familiar, because recall in the previous slide, the value of the function f of 5 at x equals 5 is the 88,372. So we can draw a conclusion of sorts, which we haven't proven yet, but we're noticing the remainder that results from dividing the function by 5 will be equal to the value of the function at x equals 5. And so this has some important significance for us. So we can call this the remainder theorem, which can be proven. And we will state that the remainder from the synthetic division process will be the value of the function at a specific input value. This remainder theorem allows us to evaluate a function at an input value without a calculator, because the numbers are typically smaller when you're using synthetic division than if you were evaluating at particular input values. So let's go ahead and apply this remainder theorem. We're going to evaluate a function, p of x, at the input value of 2. So we want to find p of 2 without using a calculator. The function p of x is defined this way. We're going to use synthetic division, so here are all of our coefficients. The polynomial function was in standard form. We're dividing by 2. And we go through the process for synthetic division. Multiply 6 by 2 to get 12 and add with negative 5. Multiply by 2 to get 14, add with negative 4. Multiply by 2 to get 20. When we add, we get 17. 17 times 2 is 34, plus negative 2 is 32. 32 times 2 is 64. When I add that with 1, I get 65. That is my remainder. Therefore, for the given function p of x, p of 2 will be 65. The remainder resulting from dividing the function p of x by 2 is equal to the value of the function at 2. So my claim is that p of 2 equals 65. Now we want to check our answer. So given p of x, the function that we've already defined, we want to find p of 2. This time we can substitute. Everywhere we see an x, we'll put the number 2. And again, we'll use order of operations. We'll start with our exponents, then we'll go on to our multiplication, and then we'll subtract and add from left to right, and indeed we get p of 2 equals 65. Now we can further check this answer by typing the function into Desmos.com and checking the graph and making sure that the graph goes through the point 2, 65, and it does.